So in part B, we are given a new experiment where students aim to determine the EMF of the battery, which is not ideal and has an internal resistance of 30 ohms. We're told the battery is connected to a variable resistor, and we change the values of the variable resistor. Therefore, we measure different values of current. In part 1, we need to write an equation to describe the circuit in terms of the EMF, current, and the two resistances. So we can simply apply the loop rule to see that the EMF will have two components here, one due to the current times the internal resistance, and one due to the current times the variable resistance. So the EMF basically has two components here. We don't even really need to use the loop rule here. It is not that complicated. We can simply see that the EMF will be split along two resistors here and here. They will both have some potential, which is given by the current through them, which is going to be the same because they're in series, multiplied with their individual resistances. And in part 2, we need to state which quantities could be graphed to yield a straight line that could be used to calculate the EMF of the battery. And well, if we consider this formula, we can factor out an I on the right side. So we will have EMF equal to I multiplied with R plus small r. And we can rearrange this for I. So this will be EMF over R plus small r. So for example, on the horizontal axis, what we can plot is 1 over R plus small r. And on the vertical axis, we can plot the current. Just like this. And in such a way, the EMF will be the slope. So in part 4, we need to determine the EMF. We can already say that EMF is going to be the slope of the graph because of this derivation over here. And then we need to plot the graph for part 3. We need to draw a straight line to represent the data. So on our y-axis, we have the current, which has units of amperes. On our x-axis, we have 1 over R plus big R, which has units of 1 over ohm. So we see the current goes from like 0 to 0.87. So what we can do is make splits of 0.02. Like this, all the data will fit. And we use almost the entire graph, which is always a good thing. It makes also plotting things a little bit easier. And for the R plus small r, well, we can record new sets of data here. So we kind of have to calculate this every time. So for example, for the first one, you do 1 over R plus big R. So the first one would be, for example, 1 over 30 plus 200. So this will give us 0.0043 approximately. And then we have 1 over 30 plus 300. This will be 0.0033. And then we have 1 over 30 plus 450. This will be like 0.0021. And then we have 1 over 30 plus 700. This will be like 0.00137. And then we have 1 over 30 plus 1200. 0.000813. All right. So what we can do here now is plot each of these values. So for the horizontal axis, we can take a scale which should be kind of small. It could go like 0.001, 0.002, 0.003, 0.004, 0.005, and finally 0.006. And what we need to do now is plot each of these values. So, well, the first point is going to be at, we could start either way. We could, if we want to start from the bottom, then we should start with the last row here. We could also start the other way, but 0.016 and 0.0008. So that will be approximately over here. And then the next point will be approximately here. Again, I'm going from down to up in this case, just so that I can go from left to right in the graph. The next point will be approximately here, then here, and then over here. And then we need to draw a line of best fit. So we can see that it's going to look approximately like this. Nice straight line. And then all we need to do now is calculate the slope to calculate the EMF for part 4. So, well, we have to select 2 points on the line. It's important that they're on the line, not necessarily the points we plotted. It just has to be on the line. So we can really select any points here. For example, we can select the point at 0.008 amps. So this point over here, maybe I'll symbolize it with something else just so that it stands out. So I'll select this point, and we can select this point, which are right on the big axes intersection points. So then it will be 0.08 for the change in y, minus 0.04, and for the change in x we have 0.004 minus 0.002, and this will give us 20 volts for the EMF of the battery.